the motto of this lecture is to motivate the student to pursue mathematics. This is first agenda, and second agenda is this kind of lecture series will definitely help them to crack, or maybe it will kind of motivation to solve the IIT JAM questions, or might help them to pursue the higher education in the IITs, not only IITs, the exams, competitive exams related to MSc Mathematics. So this lecture series, I'm sure that will help them to increase the competency in mathematics. And one more reason to start this lecture series is that BK Birla College is celebrating Golden Jubilee year this year. So we are to commemorate our Golden Jubilee year. We department has planned to conduct this lecture series. So from entire department, sir, I welcome you, and I request Gajanan sir to give you a brief introduction, and then after Nitin Poddar sir, you can take your session. You can start your session. Thank you.
Am I audible, sir? Prakash sir?
Yes, sir, you are audible. Right, sir.
Yes, you are audible.
Okay. I am very happy to introduce today's speaker, Professor Nitin Kumar Poddar, sir. He has completed his MSc from IIT Mumbai. He is an associate professor in Ruya College, Mumbai. His area of specialization is analysis of partial differential equations and rational mechanics. Sir has published 4 research papers and also completed one UGC project. Now I request Sir to start the lecture.
Yes,
Nitin
right.
sir, over to you.
Yes, thank you, sir. Thank you very much. Gajanan sir and Prakash sir, thank you very much. Our, colleague is also there, Saili Kumthekar, Saili Kamlapurkar, and rest of the other colleagues are also there. With your kind permission, let me just see. Is there any mechanism by means of which I can get responses from our students? Is it possible to have it to have such a thing?
Yes,
Whether
sir. Yes, sir.
they are getting or not. They can unmute themselves in between and they can raise the question. They can ask the
Sure,
question.
sure, sure.
Yeah.
Yeah, yeah,
Yes, sir.
that is allowed because we have kept an option open to student that they can mute. So that option has been kept open to student. Even there is a
Wonderful.
chat box. So if they wish, they can even write down the chat box. If
Right.
they want to raise their hand, there is a raising hand option. So in between, they
Okay.
can raise hand also to ask the query.
Yeah. Yeah. Right. And yes. See what. I would like to start with only one simple question. Uh, shall we assume that every one of us knows the traditional Taylor's theorem, the one which we are learning since our first year of BSc, right? Shall we assume it so that we can discuss fine details of the Taylor's theorem? Okay. Once you are prepared, uh, just let me know whether we can assume the Taylor's theorem or not. Okay. If not, then we can even start from the scratch. That is not a problem. Okay. And I really have in mind not just a single lecture, but 2 to 3 lectures, so that you and me. Just a second. Yes, we can share our ideas, right? And we can have a nice discussion on these topics, right? Particularly Taylor's theorem. I will. Where did it go? Yes. So first of all, let me tell you uh, what I think about these kind of examination. First of all, let me tell you, as far as marks are concerned, I was really not good since my childhood. But one thing is certain, right? There is a drastic difference between clearing a competitive examination and passing in a traditional examination. One stark difference is that in traditional examinations, the examination which you appear in your college, in your school, at the end of the semester, uh, you are expected to know minimum working knowledge. You must have minimum working knowledge. What does that mean? That means you will be asked exactly the questions which are from the syllabus, first thing. And second thing, mostly you will be asked the short answer kind of things, so that it is not difficult to write the answers. Okay. And once you have understood it, then you will able to write the answer. And even if you have not understood it, you can just by heart it and reproduce it on the paper during examination. Okay. But there is so in other words, our traditional examinations, the examinations which are conducted at the end of the semester or year, they are conducted to pass you, to to make you through the examination and to let you admit in the next year. Whereas these competitive examinations of, I mean, competitive examination of any kind, right? They are altogether different, right? They are meant to be shortlisted, right? There are limited places, there are limited seats, there are limited vacancies at, say, those places where you want to go in, whereas there are many students who are willing to occupy those seats, right? And that is why it becomes necessary to order these students according to their knowledge. And then one is not expected to know minimum working knowledge, but one should have sufficient enough idea, sufficient insight into the topic, so that he will able to answer the questions which will appear in the examination. That is competitive examination. Say JAM or any MPSC examination or UPSC examination, right? Or any other examination, which is competitive one, where several students are getting, I mean, are applying for the test, whereas very limited students are needed to be selected in order to place them, maybe say for admission in MSc or some job like MPSC or UPSC. Okay, therefore, uh, you must have sound foundations before you start preparing for these examinations, right? I mean, along with the text which is given in the book, you should have your own opinion. You should have your own opinion about the topic in the text. Okay, what does that mean? And in next one or two lectures or two, three lectures, we will try to understand these nitty-gritties of having insight into the topic. Okay, right? See, when you appear in an examination like JAM or NET or MPSC or UPSC, one thing is required. What is that? You will have, I mean, the question, the or the problem requires one single idea to get it cracked, and it is your insight that will decide whether you are going to crack that idea. Uh, you are going to uh, have a snap of that idea in your mind when you are reading the question. Okay, see, each question will I mean, will consume say 1 minute or 2 minutes or perhaps 1.5 minutes, and in those 2 minutes uh, that idea should strike you and you will get the answer. Okay, now, what happens? There are variety of things which appear in mathematics, especially in case of calculations. Okay, if we have misunderstood the concept, then generally it happens that we are going to commit uh, a kind of mistake which are finitely many, so that the one who has saved the paper know that these kind of mistakes are generally going to get committed during the examination, and exactly they will also produce those answers. And out of those four questions, once the answer which you have obtained, if you find it in the options, then you will immediately tick it. Okay, and we are trapped. So point is that having sound foundations, good insight into the topic is very necessary to avoid mistakes which actually may keep you away from your objective, right? So you have to be very thorough with the topic which you are studying. And in my objective in next 2 to 3 lectures, perhaps only the 2 lectures, is to let you know how to study calculus, how to study analysis, right? My way of looking at things is slightly different, since my area of research, or the things which I study, they are essentially from uh, mostly from philosophical kind of things, and they have really little relevance to the traditional way of doing things. Anyway, I mean, you will come to know slowly what I mean. Okay. Now let us talk about. Let us come back to the to our subject. And fine. It is Taylor's theorem that we want to understand, as the title suggests. But Taylor's theorem is one of the central issue, actually. Okay, it is a theorem. Okay, it is known result, but Taylor's theorem, in my opinion, is one of the central issue in mathematics. Okay, not just in mathematics, but meta mathematics also. What does that mean? That means our objective. What do we do in mathematics, and particularly in calculus? Let us. Yes. Uh, yes. Is there any question or doubt you would like to ask me? Subrat? Subrat want to ask me? Yes, Subrat. Subrat, you want to ask something?
ಎಲ್ಲೋ ಅಂತೆ ಇಯರ್ಫೋನ್ ಇರ್ಬೇಕು.
Okay. Fine. I mean, you can always unmute yourself and ask question. Huh? There is no difficulty with that. Anyway, let us come back to our calculus. Right? Uh, in calculus, there are, I mean, two uh, main words which we will discuss, and then we will go further towards Taylor's theorem. See, we are talking about first, at least to begin with, real valued functions of a real variable, right? And what are we going to discuss is this. I hope the screen is visible to you, and it is. Let me just see. Okay, right. It is this fx is the one which is of our interest, right? Now x takes values in certain domain, okay, and fx takes values in codomain, right? Is the screen visible to everyone? If it is, then we will go further. Huh? Yes,
Yes, sir.
right. Yeah. So let us take interval AB. Okay, and what I will do, I will define a function f from AB to R. This is of our concern. Along with that, sometimes we also deal with functions which are purely defined on the open interval, right? Which are purely defined on the open interval. Now we will try to look at the word local. Okay, right? What is f? F is a kind of information at a point x0 belonging to say AB, right? And f of x0 is this information, right? Now, point is that behavior of f in the neighborhood of x0 is the one that we are interested in, right? Behavior of f in the neighborhood of x0 that we are interested in, and all those properties whichever may exist around f, right, purely depending on the neighborhood of x0 are the one which are known as local one. For example, derivative. Right? Derivative is a local property. What does that mean? Means f dash x0, by definition, what is it? Limit h tends to 0, f of x0 plus h minus f of x0 upon h. What does this mean? This means I should have function f defined in the h neighborhood of x0, first thing, and then I compare value of f, right? How does it changes around x0, isn't it? So it is like this. So this is our neighborhood x0, and somewhere at this point I will find x0 plus h. See, this is x0, and somewhere here it is x0 plus h, here it is x0 minus h, and my objective is to study properties of fx, right? Depending how f changes, how f changes in this interval x0 minus h to x0 plus h, and then I conclude properties of f. What are the properties of? For example, if f dash x0 is greater than 0 at x0, means actually what? Means this limit h tends to 0, f of x0 plus h minus f of x0 upon h. This limit is greater than 0, right? This limit is greater than 0. What does it mean? It means actually f of x0 plus h is, oh sorry, greater than f of x0. And what does that mean? That means in the neighborhood of x0, right? Actually, I mean towards h. Actually, when we define limit, then it is right hand. I'm coming to that point, but my contention is that f is increasing, right, at x0. Okay. Now, when I say that at x0 is same as in the neighborhood of x0. Right? Is the meaning of the word local clear to you? When I say something is true at a point x0, means actually it is true in the neighborhood of x0. All right. That's what the word local means. And the second question is, so for example, increasing, we have this test that f of f dash x0 is greater than 0, means f is increasing at x0. Okay, f is increasing at x0, and that is in the neighborhood of x0. This is what local means, right? But at the same time, if I say that f x, right, plus h is greater than, let me write here, h means very simple, f of x plus y is greater than fx for all y greater than x, right? Isn't it? For all y greater than x, then f, this is not just at a neighborhood, right? But on an entire interval, this property is expected to hold true, and then a situation becomes global one, right? Then we are trying to understand it's a global one. Now, for example, I can raise this question, right? Let us ask ourselves this question. Let y is equal to fx, okay, be a differentiable function, right, in the neighborhood of, say, open interval, let me say r, okay. And what I'm saying is that f dash x is greater than 0, right, for all x greater than 0, right? Does it mean that fx is increasing, right? Does it mean that fx is increasing, right, on r, right? And what we do, so instead of writing for all greater than 0, you can even say that at each x greater than 0, right? Does it mean that fx is increasing on r? So yes, and but then it requires a proof. Then it requires a proof. At the same time, let me write a second statement. Okay, every one of you know this thing, right? Limit n tend to I'm introducing one sequence, real sequence n upon n is equal to 0, right? If this sequence n equal to 1 to infinity is bounded, right? is bounded sequence, right? So here also this requires a proof, right? Isn't it? Right. Yes. So this requires a proof. Now, local information, okay, say like derivative, we want is given, okay, local information is given like derivative, right? How to extract, how to extract something global from it, something global from it, right? See, in last few minutes, oh sorry, I have given you two questions, right? What did I say? That f dash x is greater than 0, right, at each x, right? Then fx is belongs to R, of course, huh? And let me write here, say for a while I make it 0 to infinity, then fx is increasing, okay, on R, right? The derivative is at a point each x, whereas this conclusion is on R, right? Then second thing I have mentioned is this one, limit n tend to infinity an upon n is equal to 0, right? And it requires a proof, isn't it? This is another thing which I have written. Now look at here. In earlier case, our domain of definition was say 0 to infinity, open or close. That is not so much important. And in this case, our domain of definition is sequences, right? I mean set of natural numbers, set of natural numbers. And what we do, we prove that this sequence. I mean, if I want to prove that limit n tends to infinity, n upon n is equal to 0, and of course it is assumed here, provided n is bounded, right? Then I need to prove that it is first of all a Cauchy sequence. I mean, these kind of things we need to do, right? Every one of us knows it, isn't it? But what you know is that algebra of convergent sequences, right? Algebra of convergent sequences, isn't it? What every one of us knows is that algebra convergent sequences. But when such a thing is required to be proven, then what we do, we write n plus 1, for example, and then n plus 1, and then n upon n. Actually, one should write m, right? And then what we do is we write n plus m into n minus n into n plus 1 and upon n plus m into n, right? And now we use boundedness, that n is bounded, so it has upper bound, n plus m has upper bound, so put this upper bound here or lower bound here, right? And then we plug them here, so that what do we get is actually nm and nm will cancel, m, capital M remains, n plus n is there, and then n is there, and then you argue that this sequence is indeed converges to 0, right? Isn't it? I mean, that is boundedness. Tacitly, intuitively, we immediately can say that since n is bounded, therefore n upon n is going to converge to 0. But that's not the way to look at things, right? You should explicitly prove the sequence is Cauchy sequence, and then take its lower bound, upper bound, and then sandwich it in between, so that what you will get is it becomes Cauchy sequence, or in general it becomes like m, capital M is a constant, and this sequence m upon n plus m into n, this obviously goes to 0 as n and m tend to infinity. Anyway, so these kind of things are there which are required to be proven, right? So again I come to the same question, that here For example, in limit n tends to infinity, a n upon n, while proving it 0, our domain was domain of natural number. I mean, set of natural numbers, isn't it? But and again, of course, provided is bounded, right? Then this is first statement I'm making, and this is so domain is range of natural set of natural numbers. And second statement I'm making is that let's look at it. N is equal to 1 to infinity, and what I have done is a0 is a first entry. This is strictly greater than or equal to 0, and then a n, okay, uh, let me make it greater than 0. And my what I'm saying is that an is less than an plus 1 for each n. Okay, what does this mean? N is less than an plus 1 for each n. Here also we conclude using induction that an is strictly greater than 0 for all n, isn't it? Right, for all n. So what has happened? We have a0 is greater than 0, and if an is greater than an minus 1, or what is the same thing as an plus 1 greater than an, right, then what we say, what we argue is that n greater than 0 for all n. This is another kind of a global result, right, where our global one is set of natural numbers, right. This result is true for all n, and this is true for each n. Yes. So depending on whether our domain is discrete or continuous, right, things does change, true, but this notion remains. What is that? That when we are talking in general about natural numbers, that is sequences, then we use principle of induction, right, to extend results from, I mean, to argue about all natural numbers, right. In the same way also, we can think of continuous induction, which I will come to about it. Continuous induction on R, or on closed interval AB, or R, or set like this, or 0 to infinity, depending on it, right. Yes. So what do we do here? Okay, what do we do here is the following. In case of this one, in case of sequences or recursion or finite induction, what do we do? If I have first element, which also some people call least element, then if I have nth element, right, then I have a mechanism to go to the n plus first element, right. This is what is our induction, isn't it? And then we argue on the basis of this principle of finite induction results on entire set of natural numbers, right. This is the one what we do. But exactly same thing is expected in obtaining global results, right. What do we do here is that we have, in case of, I mean, let me phrase it in a proper way so that it will become clear. What I'm saying is that f of, okay, let us say f is a function, okay, f is from closed interval ab to r, right, and what we are assuming, first condition is that f is continuous, oh sorry, on AB, close interval AB. Second thing we assume is that f is differentiable on AB, and third thing we assume for a while is that fa is equal to fb, and the then conclusion is that there exists C belongs to open interval AB such that f dash C is equal to 0. Yes, this is what is your Rolle's theorem, right? This is what is your Rolle's theorem. Now, existence of this C, right? let me tell you the existence of this is a kind of a global result. Okay, we are not arguing about where this C will be found, how many such C's will be found, but there will be such a C, and existence of this C in this case of Rolle's theorem depends on the closed interval AB as far as continuity is concerned, and open interval AB as far as continuity is concerned, and as far as differential open interval as far as differentiability is concerned. As far as differentiability is concerned, right? I mean, see, this C, which is guaranteed in Rolle's theorem, is a function of, say, this. Okay, this C is a function of AB, right? Means what? Means if I extend B to say, if I extend this B further, if I extend this is A to B for that matter, and if I extend this B further, right, then the, I need additional information, and I just cannot say that just this B can be made to somewhere B plus H. Okay, and still your Rolle's theorem will be true. Okay, Rolle's theorem will be true with the sole hypothesis given on these 2 points and its differentiability in the open interval, right? It depends on the interval. That's what global means. Means what? And if at all I want such a result to be extended further, okay, what I need some mechanism to go from B to B plus H, right? What does that mean? In the case of natural numbers, I should have mechanism to go from n to n plus 1. This is what we call induction state. Okay, induction state. And here also B to B plus H is also your induction state. What is difference? Difference is that of openness, right? In n to n plus 1 is our usual thing. Just increment by 1, and that is what to make myself more clear, I am giving another example to you. See, I hope you have got the point. If some result I have about a function f on the interval a to b, then question is it possible to extend it little bit ahead of b, okay, on the right of b, correct? This is the same thing as we do when in case of induction, right? I want to go from n to n plus 1, and if I can do that for general n, then result is true for all n. If here this b can be any arbitrary real number, and if I choose it once, like the n is chosen, if I can extend it epsilon neighborhood or h neighborhood ahead of b, then it becomes your true result. Okay. Now, story doesn't end here. Why story doesn't end here? I will come back to this point again. Let me give you an example. See, you know the series, right? What do we do here in the integration? I'm coming to Taylor's theorem. Okay, I mean the main problem, the fx dx is your integration, right? What do we do here? This dx is there, right? What is this dx? Dx is nothing but x plus dx minus x actually. Okay, and what does this mean? This x plus dx, this fellow is somewhere here. Okay, and this is your x, and somewhere here is your fx. Okay, and you take this your fx is here, right? And this is your somewhere here it would be fx plus dx, and you take this rectangle and then find the area, right? And dx is nothing but infinitesimal, so dx becomes smaller and smaller, and then your entire area can be calculated, right? So this is our integration. Same thing holds true. What did I wrote there? X plus dx minus x, right? And in case of our traditional induction, what do we do? N plus 1 minus n, right? Summation, say an, and this is your 1, right? And this is nothing but domain I am not prescribing because that is not so much thing. N plus 1 minus n, right? So this is your infinitesimal in some sense. in the case of series, in case of discrete structures, whereas in case of continuous structures, your dx is the infinitesimal, right? How meaning changes, that also we will see. But point is that here also it is summation. This s means sigma, okay, or summation, and you sum over small intervals, and as small as possible can be brought in, then it becomes integration. Whereas when you restrict yourself to n plus 1 minus n stepwise increments, right, then it is your series. Okay, then it is your series, right? So in this sense, this series and integration, they are actually equivalent, and the atomic element 1, okay, plays the role of infinitesimal or a small quantity, okay, right? And okay, I mean more about it will come there. Okay, now I'm trying to see, coming to the Taylor's theorem. Okay, before that, I think I should give you one illustration of how continuous things behave, right, with respect to increments. So I will simply prove one result, and let us see whether you appreciate it or not. What we will do, fx is there, okay, is a function, and what I'm saying is that f of x0 is actually greater than 0, and what I'm saying is that f dash x is greater than 0, okay, for all x greater than x0, right? And then I can prove that f of x is strictly greater than 0 for all x greater than x0. Okay. So this is also a kind of thing which is required. So what we do here, how we argue here is that I mean this is what continuous induction means, right? Means f of x0. See, this is my x0 and this is your y-axis, and something like this is your function, okay, and f of x0, this fellow is greater than 0. My objective on the lines of f of x is greater than 0 for x is greater than 0 is to extend it further, okay, say x0 plus h, and then I draw a graph, and then using our traditional technique, what we prove is that the slope at x0 plus h is given to be positive, but then also I can argue up to x0 plus h that it is indeed greater than 0, and whatever thing I have argued about x0 plus h, like this, this is open interval here, that can be made into a closed interval. Means what are we doing is this, that f of x0 is greater than 0 and f dash x is greater than 0 for all x greater than or equal to 0 for that matter, then actually f of x is greater than 0. This is the same result which I stated, that n a0 is greater than 0 and a n is less than n plus 1, this kind of thing. And then we argue that for all n is greater than or equal to 0. Sorry, strictly greater than 0. Okay, and of course f dash exists, and so these things work. Okay. So what is the moral of the story? Moral of the story is that ultimately what we want to do. Let me just make my this screen. No, where did it go? Just a second. Huh? No, this is. Let me just see. Clear. I'm making all frames clear. Just a second. Huh? See, you please raise the question when you want to ask. Okay, I will put now. I mean, I will put things in perspective so that you will understand it. Okay, I mean, what I'm trying to tell you. see, we are too young to understand formal things, and we tacitly try to assume the results around us. But my contention is that we should try to think a little more in form. We try to learn how to argue formally. Okay, so I will state it here. Okay, mm, uh, continuous rather than the. Okay, so I will state the result. What happened? Right. Okay. So see, uh, we wrote Rolle's theorem, and before that, I mean, along with that, you also know one property of uh, intermediate value theorem. What does it states? You know that if f from AB to R, okay, if f is continuous at x0, I mean at x belonging to AB, right? For all x belong to AB, then mm, for each y belonging to FAB, say there exists x such that belong to, of course, AB, such that f of x is equal to y. This is intermediate value theorem, right? Isn't it? Means every value should be taken there. And now one result I state is if okay, let f from AB to R is a given function, f is differentiable on AB, then everyone knows that f may not be continuous, but still f dash will, or f dash have IVP on open interval AVP. Okay, even if f is just f is differentiable on AB, f dash may not be continuous, but still f dash will have an intermediate value property on the open interval AB. Okay, this is you can prove this result. That wouldn't be a difficult part. Okay, but f dash will have an IVP, right? Isn't it? So what we have done so far? What we have done so far is what we have done so far is that f we have stated Rolle's theorem. We have stated that if f is a differentiable on AB, then f dash have intermediate value property, right? Another intermediate value property we will state now is that let f be uh, integrable. Integration means Riemann integrable on closed interval AB. Okay, then actually there exists S belongs to AB. Okay, such that your integration A to B f of t dt is equal to f of s into b minus a. Okay, this is another intermediate value theorem. Okay, this is another intermediate value theorem which we will use, right? There exists S belongs to AB such that integration from a to b ft dt will be fs b minus a, and the similar theorem can be stated further. Let f g b say Riemann integrable on AB, okay, and G is increasing on AB, okay, then point is that integration a to b f g dt would be equal to f of s a to b g of t dt, okay, and then there exists s, okay, there exists f, of course, belonging to the open interval AB, such that integration a to b f g dt is equal to fs into a to b gt dt. What is expected is that g should be increasing here, okay, g should be increasing here. This is another intermediate value theorem, okay, and now come back to this. So what do we do here? See, it is like this. If I mean f is a function from AB to R, right? Then, I mean, now I am not imposing any condition of first of all, but just conceptually, what is clear is that f of t is equal to integration a to t f dash x dx. This is your fundamental theorem of. This is our fundamental theorem of yeah, calculus, right? F of t equal to a to t f dash x dx, right? And what we do here, this is plus fa, plus fa, right? Once this is done, but this also you can write like f of t minus, sorry, f of t minus f of a is equal to a to t f dash x dx, and what this will give rise to, if you use your earlier intermediate theorem, this will give rise to f of t minus f of a is equal to f dash s t minus a. So what did I do? I tacitly said, I mean, just naively, I mean, without imposing any condition, fundamental theorem of calculus says that f of t is equal to integration a to t f dash x dx, right? And of course, plus fa, and then what I do, I bring this fa on this side, f of t minus f of a, and this is nothing but your a to t f dash x dx, right? And this will be equal to, using our intermediate value theorem which we stated, is f dash s. So we write f of t minus f of a is equal to f dash s, and what this is t minus a, right? And this is nothing but your Lagrange's mean value theorem, right? This is nothing but your Lagrange's mean value theorem, and I will just clear this. So there exists s belonging to where, a to t, okay. Open interval I am making a to t, okay, such that f of t minus f of a equal to f dash s t minus a. So let us put this in a context here. So what we have proved is that if fundamental theorem of calculus is applied to f, and f has derivative, then only then we can apply, of course, a fundamental theorem of calculus. Then what we get is f of t minus f of equal to f of a plus f dash s, right? F dash s into what? Into t minus a, and this s belongs to a to t. This s belongs to a to t. right? Now question arises. Okay, now question arises that what is this S, right? Isn't it? Now in the since the beginning, I'm insisting on one thing, that this S depends on the interval. Okay, I mean this S gives us a global information about the domain. See, in other words, what we can think of is this S. Okay, yeah, itself. As okay, as t tends to A, right? S tends to whom? S tends to also A. Okay, this is a kind of continuity is there, but when I write, what was the assumption? Assumption was fundamental theorem of calculus, one thing, and then what was this is one assumption. That is, this is a part of our theorem hypothesis of the theorem. This is given, right? And f dash, f is a primitive of f dash, isn't it? So it is a very strong result that such a thing can be done, and it boils down to s. I'm simply writing this you to emphasize sorry, I made a mistake actually. A to t, right? S belongs to A to t. In the open interval at, right? Point is that if I take s equal to a, right? If I take f of t, okay, look at it, f of a plus f dash s t minus a. Point is that when I make this t tend to a, right, what happens with this f dash? Okay, or what can I say about this s, right? Now, as t is made to tend to a, this s will also move towards a. Okay, what will happen is that see, if this some graph is there, and this is your a to t, okay, and this s is calculated by some means, then uh, this s will be somewhere here. Okay, somewhere here, and this s has to be when t will be made to tend to a, then s will also simultaneously will tend to a. Okay, right? This is not traditional things. You will find this thing in every book. That is not a problem. Problem is that we have assumed, our hypothesis is that fundamental theorem of calculus, right? And not every time, this kind of things does exist. That is, in the next slide, it will become clear that this this is A, this is T, this is your open interval, somewhere here is the S, okay, and as T tends to A, let me write here, T tends to A, then S tends to A. We need to prove this, first thing, and second thing is that can we make T equal to S? And this is where this earlier part I was trying, this is where your continuous induction will come into picture. I'm showing it to you. Okay? I'm immediately coming to the point. What we do is f of t is equal to f of a minus, plus f dash. Again, I take a here, it will be your t minus a, and then here it will become f double dash s upon 2. This will become t minus a square. Okay, this is the thing which I have applied, okay, to whom? To the second derivative. Okay, fundamental theorem of calculus when applied to second derivative will give rise to this result. Again the same thing, if I write here f of t, if I apply fundamental theorem of calculus to third derivative, then I am expected to get fa plus f dash a t minus a, right? And plus again this will f dash will come here, and I will get t minus a square upon 2, and here I will get f triple dash s upon 3 factorial, and this will become your t minus a cube, okay, right? And this is error term, this is error term, and these remainders, right? F double dash s, f triple dash s, they depend because this is derivative on the values of f at those points. But every time, right? This fellow s, which is existing, for example, in the when you apply first time the fundamental theorem of calculus, the s which you get depends on the TA. When you apply second time the fundamental theorem calculus, you get the S dash, is also belonging to TA, right? And in the third time also is there belonging to TA every time, okay, depending on the number of times you are applying your fundamental theorem of calculus. But on whom it is depending? It is a function, some kind of xi of t of a, xi of t of a, xi of t of a, right? It is every time. It is a function of the interval on which you are applying actually fundamental theorem of calculus, right? And then what is our point? Since the beginning, what I am trying to explain is the following. What happened? Okay, yes, this is the thing. I'll just clear the frame. What I'm trying to tell you is that our objective is that it is fine. I mean, f has certain hypothesis on it, or might be explicitly given, and it is defined on the interval, say AB, for a while, okay, to make things uh, right. What I am trying to tell is that you have this so-called expression, right? Ft is equal to, I mean, let me write it directly here. F uh, uh, F, we write it as a k, then a upon k factorial, okay, and then I will write here t to the power k, and this will be k equal to 0 to say n minus 1, and then plus 1 remainder term, right? R a, and this depends on it. Means the point where you have started, it depends on a, and the derivative, the order which you have taken, and our point is that how this RAN, this RAN will contain actually that fellow, right? S, F, and S upon S factorial, sorry, N factorial, and this will be T to the power K, and this FNS, nth derivative, of course, FNS, this is, I will give you problems and some illustrations such that our objective will be to extend this t, the variable t, right? Where this formula is true, this formula is true on the interval generally a to t. At a there is no problem at all because everything is fine, right? I mean, if you put here t equal to a, then this okay, I mean here t minus a to the power k, t minus a to the power n. Okay, so at t equal to a, this only fa remains and rest of the thing becomes 0. So it is a trivial case. Okay, what is important is that in the interval and in the open interval at, I am expressing in this fashion. My objective is to stretch, to make this t a closed interval here, right? And my point is that I write again the same thing here, is that f is a function from AB to R, and we have this expression f of t equal to say f of a, and again the same thing I am writing. Just to emphasize, I am writing here fa, so that k equal to 1 to n minus 1, f k evaluated at a upon k factorial. This is your t minus a to the power k, and the plus remainder term, okay, plus the remainder term, remainder term, I mean, let us write the explicit itself as repeated application of fundamental theorem of calculus has led to this expression, and this s, okay, this s belongs to at. S belongs to at. Our objective is to make this s up to t. What happens at t? S equal to t. The behavior, I mean, if you solve this expression, then you will get s as a function of t, right? And our point will be when this s of t can be made actually equal to t, and the extent to which this t can be stretched to b, for example, or further to the infinity. Okay, and that's what I mean by continuous induction here in this case particularly. Okay, right? And when can this be done, and how this can be done, right? And that's what and that's what in the beginning itself I told you, that assume Taylor's theorem. I mean, you know Taylor's theorem, right? Since your first year, or probably for good students earlier than that, you know the Taylor's theorem, right? But what we want to do, we want to stretch, right? This, see, Taylor's theorem, every term is local, every term is a derivative, right? And our point is to continue the business up to b, in when function is defined up to b, and if possible beyond b. Okay, and how we do this? We do this by means of so-called continuous induction, and this exercise is really worth doing, because if you carry out this thing, then what are the things which you will come to know while doing this? See, we are going to understand Rolle's theorem we started with. Then we wrote intermediate value property. Then we wrote intermediate value property for integration, right? I mean, this is the property which we wrote: a to b f of t dt is equal to, actually, f of s is equal to b minus a, for that matter, right? So this is intermediate property we wrote, isn't it? Another intermediate property we wrote is a to b f g dt is equal to fs integration a to b g dt. Point is that this g is expected to be monotonic function. Okay, right? And this and then see, this is the first thing, and this is the same second, and the third thing is that I want you to understand this one. What is that? Green's theorem, right? If everything goes well, and you please cooperate with me, in that case, I will show you, okay, that how Green's you know, right? People who know several variable calculus, actually Green's theorem is nothing but integration by part. Okay, what is integration by part? Integration. So that Green's theorem I want to do, and I want to explain. It's this one. I mean, Taylor's series form of it. Okay, Taylor series form of it, which is essentially derived from this FGDT kind of thing. Okay, this Rolle's theorem, IVP, and this kind of intermediate value property, and along with that, fundamental theorem of integral calculus also will be prepared, right? So that you are applying uh, fundamental theorem of integral calculus again and again, on the assumption that so many derivatives do exist, right? What we are going to do, we are going to see, these are the things, the traditional one, right? Everyone finds these things in the book, okay? But what we want to do is the yes, or the remainder term. So let me write here, particularly here. I'm writing this statement only in one variable case. So our ft is there, is equal to, so let me write here, say Taylor's polynomial, okay, say of n minus 1th degree, right? And plus your remainder term. Okay, Taylor's theorem you are arguing on the closed interval AB. Remainder term depends on A, the first point where you are starting, and the degree derivative n. So it depends on RAN, and what, so this remainder term RAN will contain one unknown S, right? We know only one thing, that this S belongs to the closed open interval AB. Our objective is to see whether this S can be stretched to B. Okay, this S can become see, performance of S related to A is known. As T tends to A, S also tends to A. Fine, but what we want to see is that whether this S can be straight, this at B this is open, right? Can it be made closed at B? Okay, means as S can be stretched further till B, and then we will see if even it can be stretched further, say B plus H, right? And if we can do that, right, then what will happen is that we can extend everything to infinity, and this closed interval AB will become redundant, right? And your Taylor's theorem serves both the purpose of extracting information locally as well as globally, right? How that needs to be studied, and we will step by step we will proceed. Okay, step by step we will proceed. For example, I mean, it is my immediate concern that there are certain kind of series, right? Like lacunary series people call it, isn't it? For example, let me say, give you example that what is that? E to the power, and what I'm saying is x, or like this. I mean, it is my personal interest is in this series, that x, okay, 1 plus x to the power 10 plus x to the power 100 plus x to the power 1000, and in this fashion. Okay, so 10, 10 square, 10 cube, etc. This will go on, and we want to understand the behavior of this fx, for example. Okay, and see at x equal to how these series behave. Okay, in terms of convergence or divergence. Fine. I mean, these kind of questions are the one which really interest any analyst actually, and it is Taylor's theorem that lets us to analyze our given function, whether it is known in explicit form or not. But if it is provided in terms of Taylor's polynomials and remainder term, then behavior of S, right, which belongs to AB as a function of the entire interval, say AB, okay, is the one which interests us. And the questions of this kind which you may find in your entrance papers, that will also be provided to you. And Prakash sir, uh,
Yes, sir. Yes, sir. Yes, sir.
आपण किती वेळ कंटिन्यू करू शकतो?
Another 2-3 minutes, sir. We can have this problem solving in the application in the next lecture, probably.
Okay, okay, sir.
Yeah, you want more time, sir?
No, 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 no.
Yeah.
I mean, we
Because
can stop here
ideally
today. That
we
is not a
designed
problem.
for the 1 hour. We have
Yeah,
designed for the 1 hour,
yeah.
but
So
you
so
can
we
take
will
5
stop,
minutes.
and in the
Yeah.
next lecture, the particular thing I want to I mean is explain is that how this see generally what happens, say, I mean, if you have this function is there, right? 1 square root of 1 plus x, okay, you express its Taylor series, right? You find its Taylor's polynomial or Taylor series, right? And then objective is that whatever remainder term is there, how this function s depends on the interval. I mean, generally we find Taylor series only up to say 1. Okay, I mean, say let me write here 0 to 1, and generally when I find anybody of us finds Taylor series, we find Taylor series in the this interval. Okay, can it be made again equal? That requires additional argument, and the same series can be even thought about minus half to 0. Okay, that also requires argument. And not just that, can we make minus 1 to like this? Okay, I mean, how Taylor series behave at x equal to minus 1, for example, isn't it? That is known as boundary behavior. Green's theorem is known for boundary behavior, right? And the integration by part is boundary behavior, isn't it? And if you let me to explain it in further details, right, I can really go about it. So fine. I mean, how actually this is implemented in solving problems, that can always be discussed. Yes. Yes, sir.
Yes, sir. Yes, sir. Yeah, it was wonderful, sir. And we have actually gone to the root, means like with a very basic,
Yes.
the how the formula has been developed at that inclusions of that intervals and all. That's really motivating.
Yes.
So
And
now I
most,
request.
yeah. Yes, sir. Yeah.
Yeah. So please, sir. Yeah.
So actually, I mean, this is, the so-called rational mechanics or analysis of partial differential equation, it is our
Yes.
objective
Yes.
that we want to
Yeah.
extend the domains and see. Recent days, let me tell you, our one of teacher from Hyderabad has claimed that he has proved Riemann-Zeta function theorem, right?
Okay. Okay. Yeah.
Okay. He's claiming that, but people are still skeptic about accepting the proof. We really don't know. We are too small to comment on it. But point is that it is this
Yes.
basic thing. Okay, that this remainder term contains this yes or C or whatever you may call it, right? And how this C depends on the interval and whether this dependence can be stretched beyond the given situation. That is the main concern with be it Riemann-Zeta function or be it Navier-Stokes equations or any kind of problem. Okay, and I
Correct.
mean, there is no really mechanism found so far which will effectively let us stretch to the end point of the interval B, and also, if possible, further.
Yes. Yes, sir. Yes.
Mm.
Yeah, but then sometimes, in fact, I strongly feel that this problem solving along with this deep understanding is equally needed, because that
Right.
will help us. Because once they are clear with the concept, with the theory, then developing problem solving skill won't be difficult, I think. Yeah.
True, true. And actually, what happens nowadays, because of this internet connectivity and all the stuff, most of the stuff is available just, I mean, online. Anybody can get several number of problems along with solutions, okay, on internet. So that,
Correct.
but the motivation, why are we doing
Motivation
certain
and just
thing?
pure
Exactly.
science or pure theory is equally important.
Right, and these things people do not find in books, right? I mean,
Yeah,
the
yeah,
things
yeah.
which I have stated today, uh,
They are
yes,
your
I have borrowed
experiences
them,
and
true,
you whatever.
but yes, but the way they were organized here is not, you will not find it anywhere. And
Correct,
in the next lecture, when I will actually explicitly tell you the dependence, how S is there, right? Then you will see this kind of questions are too frequent in our competitive examinations. Okay.
correct.
Uh,
So
yes.
we are really eager to have another lecture, sir.
Yeah. We will see.
Maybe.
Yes. I mean, if you let me,
Yeah, yeah.
then anybody is
Sure,
any time is
sure.
welcome.
We will have in this month itself. Yeah,
Whenever
yeah.
you people, and most importantly, student. I mean, I expect student to show
Availability of
interest.
students.
Yeah.
Yeah, yeah.
I yes, actually, it is. See, I mean, getting good students is also, I mean, a matter of luck. People should
Yeah,
be
yeah,
interested,
yeah.
and they should ask questions, and that is very important.
Correct, correct, correct.
They should ask questions. Yes,
Absolutely, absolutely.
right, sir.
Yeah. Now I request Gajanan sir is there. Yeah.
Hi, sir. Hello.
हाँ
Yeah.
बोला sir.
Krishna.
Thank you, sir, for this lecture. Honorable Speaker, Professor Nitin Kumar Poddar, sir, all faculty members and students. It's my privilege to propose a vote of thanks on this event. I, Krishna Ghode, on behalf of Department of Mathematics, extend a very hearty vote of thanks to today's speaker, Professor Nitin Kumar, sir, for this wonderful lecture. I express my gratitude to all the participants and students for the attending this event. I am also thankful to Professor Prakash Sansare, head of the department, and Professor Gajanan Dhumar for their cooperation in organizing this event. And at the end, let me thank you all of you once again. Thank you.
Thank you. Have a
Yeah.
great day. Thank you very much.
Yeah. Thank you,
Have a great
Nitin
evening.
sir. It
Yes.
was just a formal introduction, formal vote of thanks.
Yes, sir.
So, yeah, you are very close to us. So,
Yes.
yeah,
And
really,
we will discuss further ramifications of these things. Okay. Yeah.
yes, sure, sir.
Right,
So,
sir.
sir, have a nice day, sir. Take care,
Thank you.
sir.
Thank you very much. Yes, sir.
Thank you, sir. Thank you so much once again.
Bye, sir. Bye.